Hello everyone, welcome back again to our class. And today we are going to focus on doing some comparisons using quantitative data that have normal distribution. I hope you got some information and some fundamental knowledge from our previous session. It was about the basic practice, basic coding in R, how to import the data into R and execute some of the key commands that you can explore our data in the R program. The difference for today is that we use an online data set that we can use and we can upload from the R. So it is easy for everyone. You don't have to upload the data from your computer as long as you want to practice R. And you can also switch later on if you have your own data set, and then you can apply all the code and all the commands on the statistical test into your R. Okay. All right. So I have already a pre-written code for you and just want to explain you line by line. And I can show you what is the key point. And by this pre-written code, it is more faster, it is quicker than our usual class. All right. So let's see together. Yeah. All right. So this is the code that I wrote, and I open our R program into my screen. Okay, and now I minimize the video so that we can see the full screen. As I mentioned before, today the focus is about doing comparison using quantitative data that have normal distribution. And the test that we are using for quantitative data that have normal distribution are the t-test groups and the ANOVA groups, because these are the parametric tests, meaning that this test can be applied when your data that you want to do comparisons are normally distributed. Okay. And another note for you all to do as well is that when you compare more than two groups of data, whether it is dependent or independent, each of the data set must have normal distribution. Otherwise, you cannot use this t-test or ANOVA. Okay? If any one of the group of the data set is not normally distributed, so you can't use the parametric tests such as the ANOVA and t-test. Okay? And we will come later on with all the tests corresponding to the non-parametric test. Okay? But today, just focus on the parametric tests, which are t-test and ANOVA. All right? Okay. For these tests, we are going to use an R-based dataset in the package mass. The dataset named car93, which is the dataset from 93 cars on sale in the USA in 1993. Okay, so first, in order to get the data for our execution, for our practice, we need to load it. And first of all, we need to load library mass. Okay, and now I execute. Okay, run this library mass. Okay, and we type data and open the bracket in order to load the car data. Okay, and if you would like to see the description of this dataset, you can use the command with the first question marks and then the names of the dataset. Okay, so when reading this, you will see all the description of this data. Okay, so here it is the dataset cars 93 in the library mass. Okay, so the description data from 93 cars on sale in the USA in 1993, and there are many variables that you can also see. Okay, so here are the variables, including manufacturers, model, types, min price, max price, and so on. Okay, so the last variable is make. Okay, the combination of manufacturers and model, and it is characters. Origin is factors. Okay, weight is pound. It is scale. All right. For us, in order to be easy and quick to recall the data, then it is advisable that we name our data into a short representation. In this case, I name the car 93 by DF. Okay, and now I execute the code. Okay, all right. As usual, if you want to do some exploration of the data, okay, you can use the command names in order to see the names of the variables inside our dataset. So we have 27 variables collected from 33 samples, which means 33 cars. And if we use command heads df, you want to show the first 6 lines of each data of the variables. And now we can execute the descriptive statistic of a variables, the variable named price. So what is the descriptive statistic? So the price variable, which is scale, we have a minimum of 7.4, mean 19.5, and max 61.9. Okay, and we can also see the box plot. How is the distribution of the data? Okay, here on the lower left. Okay, next, okay, we would like to see how many variables of the data DF, which is car 93, how many variables are quantitative, and those quantitative, how many have normal distribution. We use the Shapiro test. Okay. After doing the Shapiro test, we get the results, including the p-value. In normality checked, if the p-value is less than 0.05, then your data is not normally distributed. But when your data, the result, the p-value is bigger than 0.05, then your data is normally distributed. And then you can apply the t-test and ANOVA to the interested variable that you want to do the practice. Okay. So here we can do some of the checking with just one variable by one using this coding. Okay. So Shapiro test, I want to test the price. And then you get the results here. The p-value on the console is very, very small. Okay. So this data price, the data of the variable price, is not normally distributed. Okay. So we can exclude the price data from our practice today. Okay. And doing line by line, one by one like this, taking so much time. Therefore, we can use a command that can run the Shapiro test for multiple variables. Okay, so we use the sapply and then a list. Okay, a combination. I can concatenate variables and then the Shapiro test here. Okay, so I execute and then we can check together. Okay, the result is here. Okay, so price. Okay, price not normally distributed. Max price neither. MPG city neither. Okay. And now MPG highway, neither. Engine sign, neither. They are not normally distributed. Okay. Horsepower, no, not normally distributed. RPM, yes. Okay, because the p-value is bigger than 0.05. So I already note here, RPM is normally distributed. Okay. And then rev per mile here, also normal. And then fuel tank capacity, normal. Okay. How about the rest? Okay, length, passengers. Passenger, no. But length of the car, yes, normal. All right. Wheelbase, yes, it is normal. Width of car, no, it is not normal. Okay. So after checking, I take a note for you all that the variables that have normal distribution include RPM, rail per mile, fuel tank, length, and the DF variable 22nd to 25th. Okay. From these normal distribution data, we can practice one sample t-test. Okay. Please select one. And in our example, I use the data weight, the variable weight, because weight here, you can see here, okay? It is normally distributed, all right? Okay. For this one sample t-test, our objective is here, okay? So the objective is to compare the data of the variable weight to a value of 5,300. So 5,300, it is a hypothetical value. And I hope you remember, okay, the use of one sample t-test. What for, okay? Please go back to our previous lessons. Okay, what for that we use one sample t-test, what for pair, non-pair t-test, and etc. With the null hypothesis is that the mean of the variable weight equal to 5,300. Okay, and if that's the case, we accept the null hypothesis is the p-value of the t-test is bigger than 0.05. Otherwise, we accept the H1 alternative hypothesis, meaning that the means of the variable weight is not equal, okay? Or we can say significant different from the hypothesized value 5,300, okay? Since one sample t-test is a groups of data from the 93 cars, so we don't have to check the normality again because we just have checked it and it is normally distributed. Then we can just run the one sample t-test using the command on this line, 43 line, okay, with the command t-test, okay, and then here is the variables that you want to test. Again, the hypothetical value of 5,300. Okay, now I execute the code and the result is here. So the p-value is very small, very, very smaller than 0.05. And therefore, we accept the alternative hypothesis, meaning that the average weight of the car that we collected, that we recorded our dataset, is significantly different from the hypothetical value 5,300. All right. So this is a practical example of one sample t-test. For your own practice, please choose one of the variables that have normal distribution, okay, that I just showed you earlier, and then practice the t-test. All right. Okay. Let's move to the independent t-test, or the so-called unpaired t-test. In this example, I use the variable name length, okay, the length of the car. And this, regardless of group, okay, regardless of origin, regardless of other factor variables, okay, they are normally distributed, as we have seen earlier. So when we do unpaired t-test or independent t-test, okay, based on the variable length, okay, according to the origin of the car is made, okay. So the objective is that we want to compare the means of the car length based on the origin where it is made. So the origin here, it is a variables, which is factor variable, or we can say nominal variable. So the whole dataset, 93 samples, is divided into two groups. So the first group for the car made in the USA, and another group is for the car that is not made in the USA, or we say non-USA, okay? And for the null hypothesis, this is a short form. We say the US car length is not significant different from the non-US car length. It's not different, mean equal, okay? The alternative hypothesis that the US car length is significantly different from the non-US car length, all right? Before proceeding further, okay, we can check the normality of the two groups, the length of the car between they are made in the US and those that are not made in the US. We can use the t-applies code, okay? So this is the variables that we want to check whether it's normal or not. And the second argument here, df origin, it is the nominal variables that categorize the length of the car into two. The first is for those made in the US, and the second for those that is not made in the US. And the last argument is the Shapiro test. Okay, I execute and I get the result down here. Okay, for the car made in the USA, the p-value is 0.1189, which is normal. And the non-USA car, the length of it, okay, the p-value is 0.1553, which are also normal. Therefore, we can apply the t-test, the independent t-test, using this command, t-test, okay, df length, and then as a function of origin, and pair here equal full, which means that the two data set is not paired. It means they are independent, okay? We can run, and we get the p-value here smaller than 0.05. And therefore, we accept the alternative hypothesis, meaning that there is a significant difference between the average length of car made in the US and the length of car made outside of the US, all right? In order to make you easy to see whether there is a significant difference or not, we can do the box plot running this code, okay? Right. So on the lower right here, you can see the box plot indicating on the left box plot, it is the car made in the USA, and the length is significantly higher than the car that is not made in the USA. Okay, so you can see already. And this black and white box plot is not interesting. To be more interesting, we can manipulate, we can code our R program to make our box plot more interesting with colors. Okay, so I use this command from line 61 to 64. Okay, I run the whole code and I get this one. Okay, I get this one. All right, so it looks more interesting. And for the color, you can change here. You can put it to red and green, and you can run the code again. Then you get this one. All right, okay. I hope you understand it. Next, the practice of dependent t-test, or the so-called pair t-test. Okay. See, in our data set, car 93, okay, is made not for the sake of pair or not pair. Okay, they are just the record, okay, from maybe a random 93 cars sailed in the US in 1993. Okay, so we don't really have the exact pair sample to be used for our pair t-test. And therefore, let's create another variable to assume pair sample. And that variable, let's say it is year. Okay, a half of sample let designated to be recorded in 1990s, and the other half let designated to be recorded in 2020, so that one group is in 1990 and another group is re-recorded in 2020 after like 30 years. All right, so I append a new variable name year, okay, to the existing df by doing some concatenate of the replicated, okay, nominated number 1990 for 46 sample. The first 46 sample are designated to the year 1990, and the other 47 sample, okay, the last 47 sample are designated to 2020. Okay, so this code is to append the variable year containing the nominated variable 1990 and 2020 into our existing dataset df and run. Okay, since the pair sample, okay, the data must be equal in terms of sample size. Okay, for the 1990, there are 46 samples, but for the 2020, there are 47. Therefore, we need to cut one off. In this regard, I subset a new data set. Okay, for subsetting new data set, you can refer to my previous video, okay, about subsetting. All right. Okay. So subsetting the data that contain a new variable year. Okay, I subset it from our former df, and I take all variable here. Okay, after comma indicating nothing mean we take all variable. For sample, we take only 1 to 92 sample. We leave the sample 93rd out. Okay, so that the sample size of the year 1990 is equal to the sample size of the year 2020. All right. Okay, I execute. And here on the upper right, you can see the dataset is already registered on the working environment. All right. Okay, for the practice, I select the variable name RPM. It is regardless of group, regardless of year, regardless of origin of the data. Okay, all of the 93 sample, RPM is normal distributed. Okay, and with the null hypothesis. Okay, so the RPM, round per mile something, okay, or revolution per mile, I mean, okay, revolution per mile in the 1990 is not significant different from the RPM 2020. And the alternative hypothesis, the average value between the data in 1990 and 2020 is significantly different. All right. So as usual, to make sure that they meet the criteria to run t-test, we have to check the normality using the t-apply. Okay, and this is the variables that we want to check the normality, and this is the nominal variables that grouped the two dataset into two groups, which mean paired group, year 1990 and year 2020, and the Shapiro test, the test that we can use to check the normality of the data. I execute and then I get the result. The data from 1990, okay, it is normally distributed according to p-value 0.023. And the data of 2020, it is also normally distributed because the p-value is bigger than 0.05. And therefore, t-test is okay. All right. So now let's run the t-test in this command. All right. I execute. Okay. The p-value here is bigger than 0.05. Therefore, we accept H0. Okay. Meaning that there is no significant difference between the RPM in 1990 and the RPM 2020. After 30 years, they're not different, okay? So as before, we can do a box plot in order to see visually if they are different or not. So you can see, all right? The data in 1990 and the data in 2020, they are more or less overlap. And that's why our t-test, paired t-test, indicated that there is no significant difference between the two paired data sets. Okay. All right. So that is the paired t-test. Next one. Okay. Okay. Next one. It is the ANOVA. Okay. Doing the one-way ANOVA. Okay. So here I do one-way ANOVA. Okay. I have to correct this one. All right. So the use of one-way ANOVA, I hope you still understand. Otherwise, please check the previous video in my channel. Okay. So one-way ANOVA, we use it for the purpose to compare means of more than two groups of data that have normal distribution. Okay. In our data set, the car 93, let's just make a recall. The variable that have normal distributions are RPM, okay, rev per mile, okay, revolution per mile, fuel tank capacity, length, and the variable 22 to 25, okay. For the practice, we use here the variable name, okay, revolution per mile, based on the car, the category of car that are made with airbag, just for driver, or airbag for driver and passenger, or car that is made without airbag at all. Okay, so there are three categories of airbags, the three nominated group. So the first one is airbag for driver only. The second one is airbag for driver and the passenger. And the last one is airbag. The last one, the car which has no airbag. Okay. If you want to see, please do this code. Okay. You can type table, okay, df and airbag. All right, and execute. So we see here the car that has the airbag with both driver and passenger. Okay, the car that has just only driver, and the car that has no airbag at all. So 1993, long ago, 30 years ago, some car were made without airbag. All right. So with our ANOVA, we have null hypothesis stating that there is no significant difference between the average of revolution per mile among the three types of airbags car. And for the alternative hypothesis, we state the opposite, meaning that there is a significant difference between the revolution per mile among the three types of airbag cars. Okay, and as usual, before running the code, before running the parametric test, here at ANOVA, we need to check the normalities, okay, using the code supply here. So again, this is the variable that we want to check the normality, and this is the nominal variables that categorize, okay, our quantitative variable into three groups, and this is the test. Can run, okay. So the data for a car manufactured with airbag for both passenger and driver, and for driver only, and for no one, they are all normally distributed, okay? And again, if there is one, okay, if there is one group that is not normal distributed, then you can't use the ANOVA at all, okay? You use the non-parametric test, all right? So just remember, if you compare two or three or more groups, all of the group of the data must be normally distributed. Otherwise, you can't use the parametric at all, okay? So this is just a quick note and a quick reminder for you. Okay, now let's go to doing the ANOVA test, okay? ANOVA model, okay? So ANOVA is run with AOV. And in order to use the model for later on, okay, we name this model by M1, okay? M1 represented by this coding, okay? This function we can run. In order to get the results of the ANOVA, we have to run a summary. So the result here indicated that the p-value is smaller than 0.05. In this case, we have to reject the null hypothesis. We accept the alternative hypothesis, meaning that among the three types of airbag car, there is a significant difference between the average values of revolution per mile. Okay, there is a significant difference. Okay, right. Okay, and like usual, if you want to check visually, especially with the box plot, you can just run this code, okay, line 107 to see the box plot. All right, here, okay, we can see that, okay, let's just make it bigger. All right, or you can just zoom, okay, here. All right, okay, or maybe too big. This is good enough, right? So different types of airbag car. So the non-airbag car has a high average values of revolution per mile. Okay, so the three are significant different. All right. Okay, and to make your plot more interesting, yeah, you can do it by yourself. I have shown you one time already, so use it. Okay. All right. Another clue. So if you compare more than two groups, meaning that from three groups onward, 3 group, 4 group, 5 group, or 6 group, if the overall result, ANOVA or any other like Kruskal-Wallis or Friedman or repeated ANOVA, if the p-value of the overall model is significant, you have to do the post-hoc test in order to check whether how many pairs they are significant different. Otherwise, we don't know which pair are significant different. Okay, like this one. We don't know whether the airbag car driver, passenger, and driver only is significant different or not. Okay, maybe not. You can see here because the two are overlap, except for the none. Okay, this is just my assumption. But in order to be clear, we have to do a post-hoc test. Okay, let's see how we do the post-hoc. All right, here. Okay, for the post-hoc test, okay, we can use pairwise t-test. Okay, so t-test you know already. T-test is for parametric test for the data that have normal distribution. Okay, all right. In order to see the pairwise, okay, it's the data that we want to test, and this is the nominal variables that we want to compare. And p adjusted here, we don't use any methods. Adjusted p-value, okay, to avoid like type 2 errors or type 1 error, something like that. Okay, you can type and execute. Okay, we can see driver, passengers, airbag with driver and passenger, and with, okay, driver only. Okay, it is not significant different at all, like what I mentioned. So the first and second data, right? You can see here the p-value is 0.55. No significant difference. Okay. But for the airbag for driver and passenger with the car having no airbags, significant difference. P-value of 0.004. And also the driver only and with none. Okay. So the first to the third box plot is significant different. The second to the third is significant different. But the first and second, it is not significant different at all. Okay, so here among the three pairs, there are two that are significant different. Okay, you can see here. All right, so the first, which means the car built with airbag for driver and passengers, and to the car that has no airbag, it is significant different. A p-value of 0.004. And the car built with airbag only driver, and compared to the car with non-airbag, it is also significant different. All right, with the p-value of 0.002 something. We can check again. Okay, but for the types of car build the airbag for passengers and driver compared to only airbag for only driver, it is not significant different at all. You see, this is the way that we have to check the post-hoc test. And remember again, if you compare more than two groups, upward, 3 group, 4 group, something like that, whether it is for the parametric test, ANOVA, repeated ANOVA, or the non-parametric test, Kruskal-Wallis or Friedman test, if the overall result of your test is significant different, you have to do the post-hoc test, okay? You have to do the post-hoc test in order to see how many pairs that are significantly different. All right, okay? You can do another post-hoc test, which is quite popular as well. It is called Turkey, okay, HSD, okay? You can see what is the difference, all right? Okay, here, p-adjusted value, okay? So the p-adjusted value here, okay? The default p-adjusted value of the Turkey HSD is already implemented in the default. And again, okay, you can see here, between the car that built with the airbag for driver only and driver with passenger, p-value, no significant difference at all, meaning the first and second box plot. For the airbag car with passenger and driver compared to the non-airbag car, there is a significant difference, okay? Meaning the first to the third box plot. And for the driver only, the second box plot, to the third, there is also a significant difference, all right? So the different p-value It depends on the methodology for the p-adjusted value. For the pairwise t-test here, we don't use any of them. Okay, there are many. Okay, there are many methods to adjust the p-value. You can ask. Okay, this pairwise t-test. Okay, and you will see the help here. Okay, so p-adjusted methods. Okay, you can click, and there are many. Okay, the methods here you can see like Holm. Okay, Hawkert, Hormels, Bonferri, okay, BH, and etc. Okay. Most of the widely used is the Holm correction here. Okay, the Holm correction. And sometimes the Bonferri, okay, correction. Anyway, you can search, you can do a search for this on Google. There are many answers as well. Or later on, when you have more and more experience, you can also search this. Okay. All right. That should be all for our session today. It covers the comparisons of data that have normal distribution, quantitative data that have normal distribution. We used to compare one sample, t-test, pair t-test, dependent t-test, the so-called dependent t-test or unpaired t-test, and also the ANOVA. Okay, so see you for the next video and the next practical video. See you.